Hello everyone. Today let's solve the problem number 98. Validate binary search tree. You can just go through the problem and you can just go through the examples that they have given to understand the problem correctly. So I'll just summarize the problem so that it will be easier to understand. So what the question states here, we are given a root of the binary tree. Here you can clearly see we are given a root of the binary tree and we need to determine if it is a valid binary search tree or not. We have to determine here whether the given tree is a valid binary search tree or not. If it is a binary tree, then we have to return true. If it is a binary search tree, then we have to this one. Um, we have to make use of the boolean value true. If it is false, then we have to return boolean value false. So that's what we need to do here. So let's understand what is a valid binary search tree first. So they have given some rules here. Let me read it for you so that it will be easier to understand. The left subtree contains nodes with the values strictly less than the current node. So I'll just come here. Let's consider this example itself. Left subtree is nothing but this one. Right subtree is nothing but this one. Root node is nothing but this one. So here the left subtree contains nodes with a value strictly less than the current node. Current node initially will be considering the root node always. So left subtree, this one has to be this value. Left subtree value should be lesser than the current node. So here in this case 1 is less than 2. So this satisfies the condition. Right, first condition. Second condition is the right subtree contains nodes with the values strictly greater than the current node. Means here the right subtree's value, node's value must be greater than the current node, nothing but the root node value. Here 3 is greater than 2, so this satisfies the condition as well. Second condition. So third condition is both the left and right subtrees must also be valid binary search tree. So here we don't have anything. Here we don't have anything. Let's go to the example 2, right? So I'll just come here. Just give me a second here. So these are the three conditions it has to satisfy. Here you can clearly see 5, 1, 4 they have given. Left subtree must be having the value lower than the root node, right? Here 1 is less than 5 and the right subtree value must be greater than the root node here. But 4 is less than 5. 4 is not greater than 5. Here it fails. Just give me a second. This one 4 is less than 5. So here this one fails actually. That is the reason we are getting the output false here. They have mentioned the same thing here. The root node's value is 5, but its right child's value is 4, right? So it fails the condition of the valid binary search tree. So I hope the question is completely clear. Let's discuss the approach initially, followed by this one, edge cases, one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, as usual, we'll be going with the approach. So let's discuss the approach first. So here, let's discuss the approach step by step. So here, first thing is we need to understand, we'll be making use of the recursion with range checking to validate the binary search tree, or we can just give here, we will be making use of the recursive approach. So let me give here, recursive approach. So just keep in mind, we'll be making use of the recursive approach. This is one thing. Let's discuss this one step by step. The first thing is we'll be defining a helper function. So we'll be making use of the helper function, validate of node, max, and min. You can consider any name. This is relevant to the name that I've considered here. This is relevant to this problem. So I've just considered validate and I have passed the parameters node, max, and min. Why we are considering here node, min, and max? Because the node value lies between, the node value has to lie between this one, minimum and the maximum. That is the reason I have considered the parameters node, max, and min here. We are making use of the helper function validate and we are passing the parameters node, max, and min because the node value of the node has to lie between the min and max, right? This is the first condition. So let's go with the second condition, nothing but the base case. If the node is null, then we are returning true. If node is null, then we have to return true, right? So empty trees are always valid binary search tree. Just keep this one in mind. Empty trees are always valid BST, binary search tree. Just keep this one in mind. When node is null, then we have to return true. Empty trees are always binary search tree. This one we have to keep this one in mind. Let's move on with the third this one condition. Third step, nothing but the checking for constraints. While I say checking for the constraints, let's check for the constraints, right? So if the value of the node is not within the min or max range, we have to return false. In this case, if the value of the node is not uh, not within min or the max range, then what we will do? We will return false. So this is one thing that we have to consider, right? So this is what we'll be doing, right? Next, let's move on with the fourth step. Nothing but as we have discussed earlier, we'll be making use of the recursion of or the recursive stack, right? Here we will recurse for left and right subtrees. For left subtree, we have to update for left this one. For left subtree, we have to update max equals node dot val here, value of the node. All the values must be less than node dot value here, right? For the this one left subtree, and for the right subtree, what we are doing here, right subtree also, we have to update instead of max, we have to update here min equals node dot val. Why we are updating min equals node dot value or the min equals value of the node? Because here for the right subtree, all the values has to be greater than node dot value, right? All the values must be greater than the value of the node. Here for the left subtree, all the values has to be lesser than the node dot value. I hope this is clear. The final step is we have to we have to return the result of both recursive calls. I'll just give here return the result of both recursive calls, left and right. This one what we have made use of. I hope this will be the approach that we'll be going with. I hope the approach is completely clear. Let's discuss the edge cases step by step, or one by one, and then let's write the code. Here let's discuss the edge cases one by one. First thing, I'll be going with the small tree. For the condition small tree, input I'll just consider here 2 1 3. This one will be 2 1 and 3. So left this one left subtree value is less than the root node and right subtree value is greater than the root node. Here this is valid, so output will be true in this case, right? Output will be true in this case. This satisfies the binary search tree properties, right? So the output will be true here in this case. Let's move on with the second edge case, nothing but invalid BST. So I'll just consider the example that they have given in the this one example itself. I mean question itself. Sorry, 5 1 4 null 3, 6. So here let me move on with the next this one. This will be 5 1 4 and this will be null, right? So this will be 3 here, this will be 6. So here you can clearly see 1 is less than 5, this satisfies the condition, and here this one 4 should be, I mean here this one this should be greater than 5, right? Instead this is less than 5. 4 is less than 5 here, so this fails here, so the output will be false in this case. So the node 4 is the right subtree of 5, but 4 is less than 5 here, which violates the BST rule. That is the reason here the output will be false. This is for the condition this one, invalid binary search tree. Next, let's move on with the third condition, nothing but the single node tree. So single node tree, I'll just consider here, let me write this one first. single node tree. So let me consider the input here 1. So this will be the valid binary search tree. The output will be true in this case. Why the output will be true? So I have explained this one while explaining the problem itself. A single node tree is always a valid binary search tree. So the output will be true here. So let's move on with the fourth edge case. Duplicate values. Duplicate values. Let me write this one first here. Duplicate values. So let me consider the input here. Sorry, just give me a second here. Let me consider the input. Duplicate values we are going with, right? I'll just consider here 2 to 3. So this will be invalid. So let me consider here 2, 2 and 3. So left subtree's value, node value here, this one should be always lesser than the root node value, right? So 2 is less than 2. This is false, right? This has to be lower. This has to be either 1, 0, anything. So less than this value basically. So here this fails the condition. So output will be false in this case, right? So I hope this is completely clear. This is for the condition duplicate values. Let's move on with the last edge case or the fifth edge case. Large tree with mixed valid and invalid subtrees. I'll just take this one in the, let me do one thing. Next page. So this is for the large tree with mixed valid and invalid subtrees. So large tree with mixed valid and invalid subtrees. So this is one thing. So let me consider here an example. 10, 5, 15, 6, 20. This will be the input I have considered. Here this will be 10, 5, 15. This is fine. And 6 and 20 here this will be null. So after 15, 5, 15, this has to be null, and 6 and 20 in the input. I'm just changing this one. 5. This has to be 6 and 20 here, right? So in this case, so here this one is less than 10. This is fine. This one is greater than 10. This is 15. This is true, right? So let's consider 15 here, right? Subtree, we have null here. We are not considering anything here. So this is fine. So 6 is less than 15 and 20 is greater than 15 in this case. So this is also true. Finally, all the conditions are satisfied here. So the output will be in this case true. Right? So this is for the fifth edge case. So first we went with small tree. Second we went with invalid binary search tree. Third we went with this one single node tree. Fourth we went with duplicate values. And fifth we went with large tree with mixed valid and invalid subtree. So invalid, if you want to consider here, you can just consider in this case 5, 6 and 2, something like that. The output would be false here for the same thing, right? So I have just considered valid so that the output will be true in this case. So I'll just delete this one. Just give me a second here. What happened? So I hope this is clear. Just give me a second here. I hope this is clear here. So these are the 5 edge cases that we need to keep in mind. So now let's start writing the code. So now let's write the code. As we had discussed in the approach, let's make use of the helper function to validate the binary search tree initially. I'll just be considering validate. We have discussed this one earlier itself, right? Node, min, and max. This is fine. I'm just considering const here, right? Sorry. Just give me a second here. Yeah, this is fine. First base case here is if node is null, then it's a valid binary search tree. We have discussed this one. So node is null, then we have to return true. This is because if node is null, it's a valid binary search tree. This was the base case that we discussed earlier. So next thing is we have to check for the condition. If a value should be in min and the max range. Constraints, we were checking for the constraints. If you remember, we have already discussed this one as well. Condition check, nothing but value should be in between min and max range. If it violates, then we have to return false, right? So this is simple if condition here. If value of the node is less than or equal to min, or value of the node, same thing, value of the node is greater than or equal to max. This one is similar. So then what we have to do? We have to return false in this case, right? I hope this is completely clear. Then the next step was, if you clearly remember, we have to recursively validate left and right subtrays. So I'll just give here a return. We are recursively validating, right? So let me make use of the function here, validate, function name validate. So I just give here node dot left, comma, value of the node, nothing but the node dot val here. This is fine. And again, I'll come here, I'll do same thing for the right subtree as well. So here left subtree is less than the node dot value, right? Here, this one. We have already discussed this one. So left subtree's value should be less than the root's node value, and right subtree's value has to be greater than the root node value. So here let me consider node dot right, comma, node dot val. So here I forgot to give here this one, left minimum, nothing but value should be lesser here. In this case, the value should be greater. So I'll consider max here. I hope this is completely clear. This is it for this function, helper function. So next, we have to start the recursion with no boundaries at all. So in this case, let me give here simple validate. We are going with the recursive function, this one here, validate. We are starting the recursion with no boundaries. So we are starting with root, no boundaries. When I say I can just give here minus infinity and negative infinity and the positive infinity in this case. So I'll just give here negative infinity to positive infinity. So I hope this is completely clear. Let me format the code once and let me hit the run button. So here you can clearly see all the test cases, I mean sample test cases are getting passed here. So let me hit the submit button now. So you can clearly see all the test cases are getting passed here. This is fine. Next, then the code is working absolutely correct, right? So let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is recursion with the range checking, or the recursive approach, right? So what will be the time complexity here? The overall time complexity here would be big O of n. Why the time complexity here would be big O of n? Because we know each node is visited once, as we are making use of the recursive stack, right? Each node is visited once. It leads to the big O of n time complexity. So overall time complexity would be here big O of n. And what would be the space complexity here? It would be big O of h. We have discussed this one earlier as well many times, right? When we make use of the recursive stack. Here, for the best case, when I say best case, for the balanced tree, the overall space complexity would be big O of log n because of the height of the binary search tree. And for the worst case, when we are considering the skip tree, then the space complexity would be big O of n, because we are making use of the recursive stack for n nodes, right? So here for the best case it would be big O of log n, and for the worst case it would be big O of n. So it's better to consider the overall space complexity as big O of h, because h is nothing but the height of the tree. We can just consider the height of the tree, right? So overall space complexity here would be big O of h. So time complexity would be big O of n, and the space complexity would be big O of h in this case. I hope the solution that we have written is completely clear. For now, this is it. Thanks for watching, guys.